Welcome to the 22nd lecture in Physics 10 in 30 lectures. In this lecture, we cover the last topic in Unit 3, looking at light, which follows from the unified theory of electromagnetism. We start with an overview of Chapter 11, followed by a conceptual coverage of Maxwell's four equations, unifying the electric and the magnetic fields in one consistent and comprehensive theory. A key prediction of this unified theory is existence of an electromagnetic wave, which was quickly identified with light, visible light being a small part of the electromagnetic wave spectrum. The rest of the lecture set consists of borrowed lecture videos from Physics 4C, covering geometric optics, and some illustrations of images formed by optical elements, such as lenses and mirrors. We keep our coverage at a conceptual level and stay away from involved algebra. We wrap up this lecture set with a coverage of polarization of light, which is behind the operating principles of modern electronic device displays, such as laptop computer screens. This is our last lecture in Unit 3. In the next lecture set, Intermission 2, we will look at the role of light in modern physics, alongside other content geared more at the Unit 3 timed assessment. After that, we will start our last unit of the semester, covering modern physics. Now, we start with the Chapter 11 overview. Hi, this is the overview video for Chapter 11, Light. This light chapter comes between the topics we cover in electricity and magnetism and modern physics. And that's quite deliberate because it's this light that helps us illuminate the laws of modern physics that you will see in Unit 4. Now, as we wrap up Unit 3, we introduce light as electromagnetic wave. By talking a little bit about Maxwell's equations, your textbook does that in section 11.2, and there's also a separate lecture that covers that. While talking about the details of Maxwell's equations is challenging because of the mathematical prerequisites needed to cover these laws involving calculus concepts, we'll cover it conceptually, just talking about the results of these laws and how these predict electromagnetic wave. Now, in sections 11.3 through 11.5, we look at the properties of electromagnetic waves, such as the speed of light. This is how Maxwell, the theoretical physicist who put together the four Maxwell's equations, figured out that light must be an electromagnetic wave, and how electromagnetic wave is a transverse wave, the electric and magnetic fields oscillating perpendicular to the propagation direction, and how the momentum transfer of light results in radiation pressure. There are some examples in the textbook, and I also mentioned that in the lectures. And we wrap up sections 11.4 and 11.5 with properties of electromagnetic spectra, the different aspects of the electromagnetic wave. And as you look at it, I want you to remember that these are all same light, all the same electromagnetic waves. The only differing thing between them is the frequency, low frequency, high frequency, or in other words, wavelength, short wavelength and long wavelength. And they all result in these very different looking phenomena. Now, in section 11.6, we pivot to geometric optics. This is the aspect of light that we knew a long time ago, since the time of Galileo and before. People were making lenses and working with the light without fully understanding what they are. So in geometric optics, we treat light like rays of light, that obeys certain rules, such as the law of reflection, that says the incident angle is same as the outgoing angle. And we make a distinction between specular reflection, like mirrors, and diffuse reflection, which is what you see with the most materials that's not shiny and polished like mirrors. And we cover refraction, or Snell's law, which explains in some way why light bends as it crosses a boundary between two transparent medium, and how that amount it bends can be characterized by a phenomenological parameter called the index of refraction. And in the lecture videos, I go more into how to connect this index of refraction with more first principles physical theories. And we look at lenses and mirrors, although we won't deal much with them for really two reasons. One, to actually work with what's called the lens equation. It involves a fair bit of algebra, probably more than we should have in this conceptual physics class. So we'll just cover conceptually about lenses, about converging and diverging lenses. And your textbook covers ray tracing. I don't think I covered that explicitly in any of the lectures. There is a lecture section using the PhET simulation to show you the rays, and that simulation also shows principal rays that you can use in ray tracing. So you can explore it on your own if you want. Oh, and lenses are, basis of those familiar devices like a magnifier, your glasses, and all those things. I hope people have seen lenses already before. So in section 11.9, that's where you will see those familiar devices covered in some detail. And when we look at mirrors, flat mirrors, hopefully you are familiar with them. Like your bathroom mirror. And you might have seen like concave mirrors, like makeup mirrors, that allows you to see the reflection that appears a little bit bigger, or the convex mirrors, a lot of like security mirrors and whatnot are convex. It's a diverging mirror that allows a viewer to see a wider angle of view, and radius of curvature that connects to the focal length of these curved mirrors that we skip out entirely in the lectures, but there is a simulation that you can look at if you are interested. And in connection with these lenses and mirrors, what we really should talk about are the images. I don't know why this mind map split off image type into its own thing, but this would be covered in sections 11.9 and 11.10, image formation by lenses and image formation by mirrors. So when we talk about images, there's two types, one that we call real image and one that we call virtual image. The distinction is with the real image, the light rays actually go through the location of the image. You will see an image diffusely reflecting. You will see some demos in other lecture videos. And virtual image, the light rays still appear to come from the location of virtual image, but the rays don't actually cross there. So if you place some screen at the location of virtual image, it wouldn't be projected. So it's non-projectable. And magnification, that's sort of the whole purpose of a lot of these optical devices, to magnify something that's small. So that's geometric optics covered in sections 11.6, 11.7, 11.9, and 11.10. And there are two sections remaining that's covered in your textbook, and I guess also in homework, like one or two conceptual questions that's covered under wave phenomena here. That's dispersion and polarization. It's covered in section 11.8 and 11.11. And it's under wave phenomena because how dispersion occurs and how you understand the polarization of light, you really have to, again, pay attention to the wave nature of light. So dispersion refers to how the index of refraction that we talked about in geometric optics, it depends on the wavelength of light. And because of that dependence, we can use devices like prisms that designed to maximize the effect of the difference in the index of refraction to split incident white light into rainbow colors. So that's a dispersion because it's referring to wavelength dependence. You have to have in the back of your mind, this is a wave phenomenon. And polarization, it refers to how light is a transverse wave, and the transverse, the direction of the electric field in the light wave, electromagnetic wave, that defines the polarization. And depending on that direction of the electric field, light interacts slightly differently. There are devices that's meant to kind of utilize that difference in how they interact. It's called a polarizing filter. And sometimes you get almost natural polarization that occurs through reflection. So if a polarizing sunglass, the reason you might use that is to make use of the fact that reflection tends to polarize light in horizontal directions usually. So sunglasses block that light, so it reduces the glare, improves the contrast of what you are looking at. Polarizing sunglasses, I mean. And a lot of the devices you see in everyday life, like computer screens or phone screens, they use these polarizing filters. So for light from those screens are almost naturally polarized as a result of the output filter. And sometimes that can cause issues. Like imagine looking at one of those screens with a polarizing sunglasses on. So a lot of the higher end devices like iPhones will do certain things to their screen to make the light appear as unpolarized as possible or make it circularly polarized. Optical activity, I think that's covered in the textbook that has to do with different types of sugar solutions rotating polarization of light in different directions. If you're a biology major, you might actually see this at some point. I think that has application in biology and maybe organic chemistry. So that's all the sections covered in chapter 11, light. It covers quite a bit. If you are pressed for time, you might want to look at the homework questions first so that you can get some sense of which sections you have to pay more attention to. There are some sections that I cover both in the lectures and here and in the textbook, but mostly for the sake of completeness than because you need to know it for homework questions. So this is the last chapter of our Unit 3 covering classical physics. And in the next chapter overview, we will start Unit 4, Modern Physics. So in this lecture, I want you to talk about light as an electromagnetic wave and talk about some of the properties of electromagnetic waves. So the usual starting place for introducing light as electromagnetic waves is what we call Maxwell's equations. And this is a topic that is a little bit challenging to cover in conceptual physics because it's a very mathematical law. That's why it's called Maxwell's equations. So in your textbook, the textbook attempts a description of the 4 equations that are in the set that we call Maxwell's equations. That's what you see here in the box titled the results of Maxwell's equations. So rather than giving you the Maxwell's equations, which needs calculus for correct statement, it's trying to tell you what each of those equations mean. The first equation says the electric field lines originate on positive charges and terminate on negative charges. The electric field is defined as force per unit charge on a test charge. Now, as you read this, if you think you have heard all this before, that's right. Most of this is something that we already covered in the last couple weeks as we are covering electricity and magnetism. Something like magnetic fields are continuous, having no beginning or end, that's connected to there being no magnetic monopoles. We talked about that. And changing magnetic field induces an electric field. We just covered Faraday's law in the last lecture. That's what this is. And there's one tiny piece that you won't have seen yet. In the 4th result, it says the magnetic fields are generated by moving charges. This I think you have seen described. This is what we refer to as Ampere's law, and we talked about with right hand rules the different shapes of magnetic fields produced by currents. And currents are moving charges. The piece that ought to be new is the second part. magnetic fields are generated by changing electric fields. We haven't talked about this at all. And this is what we refer to as the Maxwell term in the Ampere's law. So your textbook attempts a description, a conceptual description of Maxwell's equations. And I thought I would lecture a little bit, at least to show you the Maxwell's equations, which again have to use calculus, but at least to point out some of the patterns that you can still observe. So let me go to the infographic. So this is the infographic displaying Maxwell's equations. And in this infographic, I actually give you Maxwell's equations. This is the Gauss's law for electric fields. And it's equivalent to Coulomb's law. So when you look at this section of the infographic, if it looks like it's showing you something that you've already known, yeah, it's showing you Gauss's law, which is equivalent to Coulomb's law. So everything in this graphic can be understood in terms of what you know from Coulomb's law. Now we list Gauss's law rather than Coulomb's law because there's a pattern that we can point out. So let me just state all the other laws, and then I will highlight the pattern. So the result number 2 that was in the box that described the magnetic fields, it's actually also talking about what we call Gauss's law. But it would be Gauss's law for magnetic fields. And what I can point to is that this Gauss's law for magnetic fields, on the right hand side we have 0. And that 0 matches with the fact that there are no magnetic monopoles. So that's results number 1 and 2, both called Gauss's law. And results number 3 and 4 are the interesting things involving magnetic fields that we have covered. Let me actually go to results number 4 first, because in the kind of chronological order, that's what we covered first. We covered Ampere's law, or we at least went in some detail with the right-hand rule giving you the directions of magnetic fields. And that's what the first picture here is showing. So this is the picture that you have seen, with the right-hand rules, direction of current, if you have a straight current going this way, in what direction is magnetic field, you point your thumb in this direction. The direction in which your fingers curl is the direction of the resulting magnetic field. So magnetic fields arise from moving charges. And this is this first half of what the infographic is calling Ampere-Maxwell law. This first half involving current, this J is the current density, involving current is the Ampere's law. And we'll return to this second half after a little detour to Faraday's law, which we also talked about. So Faraday's law is result number 3. Faraday's law of induction, we just covered it. If you have some magnetic fields going through like loops, and there's a magnetic flux, and if your magnetic field is changing, or maybe the area is changing, I think this is oh, I see. So it's it's indicating this magnet, which is going to be inducing the voltage in this loop. If the magnet is moving towards the loop, then there's a flux that's increasing leftward. And the Lenz's law, which is this minus sign here, says that the voltage that's induced in the loops here, they are in such a direction that the current due to induce the voltage opposes the change in the magnetic flux. And I think you have to interpret this if you use the right hand rule. Basically, you want the magnetic field due to induced current to point this way to oppose the change. This is the Faraday's law that we just covered. It tells you basically a changing magnetic field or changing magnetic flux will lead to an electric field. That's indicated by this mathematical object. Now, when you look at the Maxwell's equations so far what we have covered, you see a kind of a symmetry that's broken a little bit, but the broken part you can explain. You see a kind of symmetry in that there's a law involving electric field that looks like this. You can just look at the shapes of these mathematical operators. And there's a law involving magnetic field that looks like this. You can just look at the shapes of operators. And you might notice that they look quite similar. Now, with the magnetic field, on the right-hand side, you have 0, but that's explained by the fact that there is no magnetic monopole. There's no magnetic charge. And these mathematical operators, they relate to the kind of fields that have this kind of shape, that look like they are either coming from somewhere or they are going to somewhere. And the mathematical operators that look like this, they are a bit of a different shape. They refer to fields that have a shape that's described by the right-hand rule. So if you have a source that is straight, then you get a field that's kind of going in circles. And if you have a source that is going in circles, that you have a field that's kind of straight. And you are continuing to see a similar kind of symmetry. There's something, current, that generates a magnetic field that has that kind of shape. And again, if you are looking for a similar term in the Faraday's law, you'll be looking for some kind of a magnetic current. And you can, again, easily explain why that would be 0, because there is no magnetic monopole. But now you have this. You have electric field that's being produced by a changing magnetic field. And if you look on the flip side here, now, before Maxwell, where we just had Ampere's law up to this first half here, you might look at it and say, I see that changing magnetic field can produce an electric field. Why shouldn't the reverse be true? Why shouldn't we have a changing electric field produce a magnetic field? And this is Maxwell's contribution to what we now call Maxwell's equations. He was the last person to complete this set of equations. So we named the whole set of 4 equations after him. He considered this scenario where you would have setup where the current is interrupted in the middle. Current is coming in, and then you have a thing that's called a capacitor. You can have a accumulation of charge on this plate, and then accumulation of an opposite charge on this other plate. And with those accumulations of charges, the current is continuing to flow through. And in between these plates, you have an electric field that's changing as a function of time as charges accumulate. And when you consider what kind of magnetic field would you have here, you get a kind of weird result if you think a changing electric field doesn't produce magnetic field. So to enforce a kind of consistency, you have to imagine a term like this exists, so that how the magnetic field appears in this setup looks kind of logically consistent. So this is the Maxwell term, one that says changing electric field produces magnetic field. And this completes what we call Maxwell's equations. With this additional term, we can now see all the expected symmetry you would see between the electric and magnetic fields. So with the changing magnetic fields, we had electric field being produced out of that. And we can flip the roles around and say a changing electric field which exists, unlike magnetic monopole, we can say that changing electric field produces magnetic field. And all the expected symmetry is there. Any kind of broken symmetry, you can blame that on there being no magnetic monopole. Oh, and I said I would point out some patterns here. The pattern is this. So all these equations are written in a way where what's on the right hand side is the source. It's the cause of what's on the left hand side. So the electric field, it's being produced by electric charge. The magnetic field, the kind that looks like these electric fields would have been produced by magnetic charges, magnetic monopoles, but they don't exist. So any magnetic fields that we have, they don't have a shape that looks like this. They might have this dipole field pattern, which you can also get out of loops of current. So yeah, there's no source for magnetic fields that have this kind of a shape. That's what result number 2 says. And with Faraday's law, there's a kind of an electric field that have a shape that obeys the right-hand rule. And the source of that kind of electric field is the changing magnetic field. And there is magnetic field that have a shape, again, that's described by right-hand rule. And that kind of magnetic field is produced by two different kind of sources. Electric current, which you can have because electric charges exist, so they can be moving, and changing electric field. So these are the sources for magnetic fields, well, all magnetic fields, and specifically magnetic fields that obey the right-hand rule. So this is the Maxwell's equations. Again, in this conceptual physics class, the depth to which we can go, it's a little bit limited because really in calculus-based physics class, so this is what I end my physics 4B class with, and what I start my physics 4C class with is the derivation of the wave equation for electromagnetic wave, starting with the Maxwell's equations. Because having this, that changing magnetic field produces electric field, and this. I don't really care about the current, but having the fact that changing electric field produces magnetic field, it gives you an interesting possibility where you could have a charge distribution or a current distribution that gives you a changing electric field, which will produce magnetic field. And then let's say that magnetic field was also changing over time. Then that changing magnetic field will produce changing electric field, which will mean, going back here, now we have a changing electric field again. That's producing magnetic field. So you could have a wave of mutually reinforcing electric and magnetic field waves. That's a possibility, and that's what Maxwell worked on, and he had the theoretical prediction of an existence of such a wave, and he derived the speed of such a wave. And when he finished that derivation, and this is the derivation that I can do in a more mathematical class using calculus, you find that the speed of a predicted wave is the speed of light. So that's the introduction of light as electromagnetic wave. And let me use the second half of this lecture just going over a little bit of the properties of light that's not covered elsewhere in other lectures. So with the geometric optics, talking about light in the way a lot of people knew since the 1700s, 1600s. I do have lectures for that, watch those. But talking about light as an electromagnetic wave, I looked through my physics 4C lecture, and there wasn't really anything that I could use for physics 10. So let me just take maybe 10 minutes talking about light as electromagnetic wave. So I got these slides here. So I generated some slides using, again, Notebook LM out of the textbook sections that correspond to this. I'm not going to read the slides out loud, but you can look at the spectrum of reality. Sure, why not? This is illustrating the kind of the wave, how a prism can split the wave into different colors. I'll talk about that by the end. So let's just start by talking about electromagnetic spectrum. So the electromagnetic wave, it exists over a very wide range of, I guess you could call it wavelengths. If you are looking at the picture that's here, there's a longer wavelength and there's a shorter wavelength, and the scale that's shown here, it doesn't do justice. The kind of the electromagnetic waves we are used to, the wavelengths for those range literally orders of magnitudes, like from order of meters to like 10 to minus 15 meters, or even shorter, of that huge range of electromagnetic waves. We are able to see a very narrow range of electromagnetic waves, which is what we call visible light. It's the range of wavelengths from about 400 nanometers to 750 nanometers, or in terms of meters, this would be 4 times 10 to the minus 7 meters. This would be 7.5 times 10 to the minus 7 meters. So it's a pretty short, hard to see scale. That's the wavelength of light that we are used to seeing. That's what we call visible light. Outside of here, either longer wavelengths or the shorter wavelengths, our eyes can't see it, but there are different ways we detect it, we experience it, different ways they are useful. I'll talk about that over the next few minutes. Now, I want you to have a good mental image for what electromagnetic wave is. This is a kind of a good mental image of electromagnetic wave. This axis is describing the direction in which this wave is propagating, this disturbance is moving, and this up and down arrows are illustrating the electric fields, and this sideways arrows are illustrating the magnetic fields, and they are mutually reinforcing. These oscillations in electric field waves that's supporting this oscillation in magnetic field wave. If you stop one of them, then the wave will stop propagating. Most of the matter interacts with this electromagnetic wave through the electric field portion. And if you absorb the electric field wave, then that will also absorb the magnetic field wave alongside. And I guess the one property that I should highlight is that this is transverse. It's a transverse wave. And this actually follows a kind of a right-hand rule. This electric field and this magnetic field, if you take a cross product between them, electric field, cross product with the magnetic field, that points in the direction of the propagation direction. And you can verify that for yourself. Do electric field, cross product with the magnetic field, use the right hand rule. You'll see that the right hand rule points in the direction of the propagation direction. That's one of the properties that you can derive mathematically. And speaking of properties you can derive mathematically, this is the speed of light that Maxwell quote-unquote predicted with his math. Now I say quote-unquote predicted because he did predict the speed of electromagnetic wave, but the speed of light was already measured experimentally in astronomical observations and whatnot. Actually, people were trying to figure out what light is. They went as far as figuring out light must be wave, looking at some interference phenomena, but they weren't quite sure, wave of what. And this almost a coincidental match, that speed of EM wave matched the speed of light, allowed people to put two and two together and say, oh, electromagnetic wave is light, or light is electromagnetic wave. And one more property of light, so it's a wave, so it carries energy, and it also carries momentum. And this is the equation that tells you the momentum that's carried by light. And I think I'm running out of time, so let me just say briefly. You can observe the momentum that's carried by light in astronomical phenomena. Like when you look at a comet named after this tail that it develops when it's near the sun, the direction of the tail, it's consistent with the direction where it's being pushed away by the radiation from the solar radiation from the sunlight. And also there was a spacecraft called Icarus project that the Japanese space agency launched and kind of did a proof of concept demonstration of solar sail that propels itself by reflecting sunlight. And the research field that I was in when I was in graduate school is called AMO physics, atomic, molecular, and optical physics. And in AMO physics, people do what's called laser cooling. cooling or slowing down atoms using laser light. And the working principle for that relies on the fact that light carries momentum. So when atoms absorb light going in the right direction, it can be slowed down. So that's another property of electromagnetic wave, that it carries momentum. Now, I'm again running out of time, but let me talk about the electromagnetic spectrum and dispersion. So in looking at the electromagnetic spectrum, it's useful to remember this wave speed relating to wave frequency and wavelength equation. You saw this earlier in Unit 2 when we covered oscillations and waves. And this applies because electromagnetic wave is a wave. So the speed of light, c, can be expressed as a product of the frequency of light and the wavelength of light. And I'm pointing this out because at different ranges, sometimes we will use the frequency to talk about EM wave in a particular range, and at other end of the spectrum, we'll use the wavelength more. And either way, if we've given you either the frequency or the wavelength, then you can figure out the other one really quickly. If we gave you the frequency, then you can figure out the wavelength doing a little bit of algebra as c divided by frequency. Or if we gave you the wavelength, then again doing some algebra, you can figure out frequency as the c divided by the wavelength. So this equation is good to keep in mind. Now the first of the electromagnetic wave spectrum, starting with the low frequency or the long wavelength range. These three laws, I'm not going to talk about that specifically, running out of time. So the long wavelength range of the electromagnetic waves are the radio and microwaves. So at this range, we are used to talking about them using frequency. In fact, AM and FM stations are often named after the frequency they operate in. FMs operate at like hundreds of megahertz. AMs operate at thousands of kilohertz. And they have wavelengths of about, let's say, around a meter, or like, I don't know, 300 meters. Like multiples of meters, that's the radio frequency. Microwaves, like your microwave oven, or your cell phone actually operates at microwave range. That's in the frequencies of gigahertz. And there the wavelength would be on the order of like centimeters. There are experiments that you can do to measure the wavelength of the microwave used by your microwave oven. It comes out to be like maybe 10 centimeters or so. So that's the longest range of electromagnetic waves that you are used to seeing and using in some fashion in our modern life. And the next range is the visible light, or the kind of the light that's similar enough for visible light that we would treat them similar. So visible light, I hope you feel familiar enough with it. And we'll talk about geometric optics in other lectures. Now the infrared and ultraviolet light, they are all slightly outside the range. So with the infrared, your wavelength is longer than the red. So the wavelength would be greater than 750 nanometers or so. And I forget exactly how long it goes before it becomes microwave, but let's say it goes at least until like 10 microns or so. And at some point, the boundary between different spectrum range becomes a little bit blurred. But infrared in this range, they kind of behave like a visible light, except we can't see them. And what kind of molecules and materials absorb it is different. That's sort of the origin of what's called the greenhouse effect. So that's infrared. Now with the ultraviolet, they are again a little bit outside this range. So the wavelength will be shorter than violet. So the wavelength is shorter than about 400 nanometers. And there's like a soft UV, hard UV. At some point, it goes from hard UV to X-ray. Again, I don't quite remember where that transition happens, but let's say at least like 10 nanometers or so might still be UV. And at some point, if the wavelength gets short enough, we're gonna call it X-ray. Now, I say all these are kind of like a visible light because you can handle them with a similar optics. You just have to be careful what optical material observes infrared and UV. Now, at the shortest wavelength and the highest frequency range is what we call X-rays and gamma rays. And these, I think we are going to see them again when we talk about nuclear physics and particle physics. So I'll just say they are really high energy electromagnetic waves. I think X-rays, people have probably heard about it, like at your dentist, medical imaging, you take X-rays, and it's a really short wavelength, less than a nanometer. I think I want to say on the order of like 10 to minus 10 meter. That feels like around the X-rays. At some point at this range, we stop referring to either the frequency or the wavelength of EM wave, but we will be talking about energy of a photon. But to talk about photon, we need the quantum mechanics that we'll cover in Unit 4. And gamma rays are quite similar to X-rays. I guess I can distinguish in two ways. One, gamma rays usually have a shorter wavelength than X-rays, higher energy than X-rays. That's one. And definitionally, gamma rays are defined as EM radiation that comes from the nuclear decay. X-rays, often we can produce them with the X-ray generating machines. With the gamma rays, definitionally, they come from nuclear decays. That's why I said we'll see them again when we do nuclear physics. Okay, now let's wrap up with a short discussion of what's called dispersion. Just because there are some homework questions that ask about how, when you see white light, just white, just a light of white color, how do you know that there are, red colors and blue colors within it? And the answer is dispersion. Imagine a prism made out of a glass material like this, and you shine white light through it, and there's a physical mechanism that causes this light of all the mixed wavelengths to spread out over a range of wavelengths. Longer wavelength on this side, shorter wavelength on this side. And the mechanism for that is what's called dispersion, combined with something called refraction that you will see covered in other lectures. So refraction describes how light bends as it goes through boundary between transparent materials. And how much it bends, it's given by something called the index of refraction. That's determined by how fast the light moves in a material. And for a glass material, you might say index of refraction is about 1.5. Now, this index of refraction, it actually depends on the wavelength of the electromagnetic wave. And this dependence on electromagnetic wavelength is what we call dispersion. And because of this dependence, how much the light bends, it depends on the wavelength. So the red light doesn't bend as much. The blue light bends more. So you can see them spread out here after they go through a prism at a kind of an appropriate angle. So I think that's the last of topics I needed to talk about. The anatomy of the rainbow, that's just dispersion. If you've seen double rainbows, it's because of like a double reflection within the material, within the droplet. You can look it up. And finally, this is the kind of the summary of what we talked about. Light is electromagnetic wave. There's an electromagnetic spectrum covering from radio to all the way to gamma rays, and there's an X-ray here that they forgot to put in, and UV, and it's kind of amazing that all these different kind of manifestations of EM wave is one thing. They are all electromagnetic waves. They are not different things, but how they interact with the material can be very different at different ends of this spectrum.
I want to show you how knowing this one expression that comes out of that 1 hour long discussion of where light comes from is helpful in making sense of what you might have had to just memorize in the past. So let me start out with something that I think everyone here has experienced seeing. And I'm saying this because I don't actually have a physical demo. I think I need to get a water tank or fish tank in the future so that I have a demo, but I don't for this semester. So the phenomenon that I'm referring to is what's called refraction of light. So the situation you have to imagine that I actually have demo for that I don't is imagine that I have a tank of water. You are looking at the tank from the side, and it's filled with water. So here's the boundary between air and water. Okay. Below here is water, and above here is air. Now, I do have a laser light, but imagine I'm shining this laser light down into that water. So there's a beam of a ray of light that's coming to here. Ooh, sorry. And what happens to this ray of light as it enters this water? Changes direction, right? Most of you somehow know this. I don't know who told you this for the first time or when you might have noticed it for the first time, but most of us know, have an intuition from just living in the world that this changes direction. And if you have thought about this for longer, what you might even figure out is that it changes direction in a way that as it goes into water, it bends towards what we call surface normal, or the perpendicular to this interface. So it'll bend in this direction. As the light comes in, this is how it bends. Right? This is an experimental fact that I think all of us here are familiar with. Right? So here's the question. Why? Why does light bend as it goes in from air to water? Imagine I'm your annoying little sibling who asks why to everything you says.
Because the speed of it changed.
Why?
The media changed.
Okay. So because the medium changed, you are saying that the wave speed is a property of medium, so you can no longer assume that wave speed didn't change. Is that what you're saying? Yeah. So that's one way you can describe it. And in fact, before people knew all of this, people could associate this bending with the change of speed at which light is traveling. You could make that argument. So this is the debate that was going on in the 19th century. They held conferences over this. Is light wave? As people like, I don't actually know their names. I know a guy named Young is one of them. But Newton was actually on the other side. If you've ever heard of Newton's corpuscular theory of light, what Newton thought was light was not wave. It was a stream of particles corpuscular. But whatever that was, both of them, what they could agree on was if light is something that travels at a speed, so in air, speed of light would be something, I'm going to use the letter C. Letter C is the common letter, lowercase c is the common letter for speed of light. I'm just going to use that. So if the speed of light in air is approximately 3 times 10 to the 8 meters per second, and somehow as it entered the water, the light slowed down, then they could come up with a model that would explain the bending, and we'll talk about that in a little bit. So the one answer to why was, well, speed of light. So this is the speed of light in air or in vacuum. Speed of light in vacuum and air are very similar. You can look at it in your textbook. They are very similar. And what they would say is that speed of light in water was somehow different. If I give a letter V to this, I don't know if I remember the water number off the top of my head. I have to, it's not quite 2 times. Let me just, it's gonna be a little bit off, but let's say it's about 2.3 times 10 to the 8 meters per second. So, so based on, this is what you might call phenomenological description. I don't know if you've heard or seen this word before. Anybody here? So this is, I think, how you spell it. Phenomenological. I think that's the right spelling. I mean, it's coming from the basic root word phenomenon. And when someone says a particular theory is a phenomenological theory, like what do I mean by this word? You could say gas laws that you study in chemistry is a phenomenological laws or phenomenological theory. What do we mean?
Based on experiment, we see some phenomena, and then we try to come up some theory to explain it.
Yeah, you start out with the experiment, and you come up with some model, any model, to fit to that theory. And this would be a kind of a phenomenological description of refraction of light. You see the light refracting, and you think, hey, if the speed of light was different here, I don't know if it is, but if it were, that would explain it. So based on that, you can sort of assign a phenomenological constant or quantity. And how many here heard the phrase index of refraction? Like that everyone has heard of, right? That's what index of refraction is. It's an experimentally determined quantity. And the way that index of refraction is defined, index of refraction, we usually use the letter N for it. Don't ask me why. It's defined as the speed of light in vacuum, C, divided by speed of light in whatever medium that is. So these two quantities are the ones that go together. This V is some kind of property of the medium, speed of light in the medium. And this index of refraction is essentially a way of expressing the exact same information. You could say, based on what we wrote down here, that speed of light in a medium is its speed of light in vacuum divided by index of refraction. So all of this is just a phenomenological description, as in, we don't have, I guess the opposite to phenomenological is the counterpart to phenomenological theory is something that you might describe as first principles. In fact, almost everything you did in physics 4A is that. As in, you start out with Newton's law, that's your basic fundamental law, and you build everything on that without introducing any more assumptions. A lot of mechanics is that, except when you start measuring friction coefficient and things like that, then it's a phenomenological again. This is what a lot of engineers do. This is what a lot of theoretical physicists like to do. And what we can say is that based on what we covered in the last hour, we can actually give a little bit of flair of how to describe this different speed of light in a medium in terms of something that's more fundamental. As in, imagine, as I said, imagine you have an annoying younger sibling who keeps asking you why. So you tell your younger sibling that light bends as it enters a different medium, because the speed of light is different there. In fact, I can even tell you that this is how they are different. This is the speed of light in the medium, c divided by n. Anybody here know what the value of n is for water? Once you know, it's an easy number to memorize. N of water is approximately 1.33. You can put one more 3 there, but that's already 3 significant figures. So after you've given all that, imagine that your younger sibling once again asks you, why? Why is the index of refraction of water 1.33? This is where we can look at this to have a bit of a more conceptual basis. That's not simply saying this is true because we know it to be true. Why is it true? Because it's true. Like, you're not explaining anything, you're just insisting that in science, that's sometimes how it works. You do the experiment, so you know what the correct result is, even when you don't understand why. But with this theory, here's how we can describe it. When I say the names of these constants, I never say permittivity and permeability. I always say permittivity of free space, permeability of free space. Why? Why do I keep adding free space? Do I like free stuff that much? I mean, I do, but what does free space mean? Yeah, vacuum. These are constants that are specifically associated with vacuum. This is the electric constant this is the dielectric constant of vacuum. This is the magnetic constant of vacuum. Water is a dielectric. So water has a different dielectric constant than air does. So what you can do is you can build an expression that's similar to this, but for light in water. So you could say this speed of light in some material is equal to 1 over square root of whatever that dielectric constant is, and whatever that magnetic constant for the material is. It's often equal to mu naught. It's usually the electric constant that changes a lot. So this is the more fundamental connection. I mean, not that your annoying younger sibling would understand it, but you can, once you make this connection, then you can actually design an experiment that would confirm for you that that is why the speed of light in water is different. You can maybe do an electric experiment, and you will see that the amount to the dielectric constant is different by actually matches it. In practice, it gets a little bit complicated because this is a function of frequency. Light is a very high frequency electromagnetic wave. And when you do electrostatic experiment, the result in, that's a complication. You will deal with it when you're actually doing physics research. But this is at least the starting point. You can connect to something that you knew almost intuitively, something that you just took on faith, to something that's more theoretically grounded. We are still on refraction. Oh, one more thing to cover. Anybody here know how what law? If someone remembers from maybe high school physics, tell me the name of the law that tells you how much this bends.
It equals sine something, right?
It involves sine. I'm looking for a name. Here's the reason I'm looking for a name. If you know a name, you can Google it. That's why names are useful. Anybody remember the name? It's a kind of funny sounding name. Sounds like a bug. Well, maybe it's not a bug. Is it invertebrate? Who here knows a lot about snails? So it's not Snell's law. Yes? Yeah, Snell's law. Let me spell it. So once again, Snell's law, you could look at it as a phenomenological law, as in people, people found that this is somehow just worked. But we can actually justify Snell's law based on our understanding of light as a wave. So this is what Snell's law says. Snell. This is how you spell Snell, not Snell. So Snell's law says, so it involves the index of refraction. And this is a good point for me to tell you how we measure angles in optics. It's kind of, I think it's a bit of an unintuitive way to do it, but that's how people do it. And I think in the long term, this is the more sound theoretically way to do it. So this is the picture of a refraction, right? Let's say I want to describe the angle at which the light is coming in. I see many different angles. I see two in particular. I see this angle here, angle between the surface and the ray, call that phi. And I see one more angle, if you look hard enough, angle between the ray and this imaginary line. Let me call that theta. Which angle, phi or theta, do you think we'll use to describe Snell's law? Theta, theta. Anybody think we should use phi? So why theta? I mean, this is such an unintuitive angle. Like even to see it, you have to draw this imaginary line. Right? What's special about this imaginary line? It's the normal. What's special about normal to a, so if this is surface, what's special about the normal to the surface? Well, sure, what's special about it being perpendicular? It's at 90 degrees. That makes it something, so let's see. This is something we were dealing with in physics 4B. Let's say you have a plane and you want to describe the plane, direction of the plane. If you wanted to associate a single vector to describe the direction of this plane, can you do it with any vector that's within the plane? No, right? So if you want to use a single vector to define the direction of the plane, that's where you use the normal. That's why this imaginary line that I drew, it's actually pretty special. When you think of this as a three-dimensional thing, there's only one line I can associate with this entire plane. So the angle between this normal or perpendicular and the ray, that's the special angle. That's the angle we are going to use to describe the direction in which this is coming in. Yeah? So that's one kind of an unusual, unintuitive thing that I have to go over. Because a lot of people, if you just got thrown into this without this auxiliary figure, you would guess that you measure this angle, and no. You draw this auxiliary figure, and you measure this angle. That's what you need to do. So I can label theta 1, and let me actually use theta naught and theta 1. So I'm using the subscripts to sort of separate out. This is the medium 1, and this is medium 0, or vacuum. And this is what Snell's law says. We do these descriptions of angle. We do this index of refraction. So I mean, if I'm being completely thorough, index of refraction of error is approximately equal to 1. It's like within a factor of, within 1 part in 1,000, it's equal to 1. So Snell's law says that this combination of quantities is constant. Index of refraction times sine of theta naught, that this particular combination of quantities that only involve quantities in one medium is constant as light goes through a boundary. That means the way it's usually given is this is equal to n1 times sine of theta 1. But the reason I wanted to highlight this first was imagine you had a third medium, and here's medium 2, and then it refracts again. Then you can actually simply chain them together. You can say, and this is equal to n2 sine theta 2. So this is Snell's law. You might have seen it in high school physics. Well, I guess if you had an annoying sibling who kept asking you why, at this point you don't really know why. Like, what do you mean why? That was in the textbook. And in a little bit, I actually want to look at this refraction picture with a picture of the wave in mind, and actually derive that it has to work out this way for things to make sense. If I have this light that's going into beaker, oh wow, you can actually see it. Let me have the water calm down first. So something else happens other than the refraction, which is the light going into beaker. What else happens? Yeah, sorry, water's a little bit too crazy, but you see the reflection, right? Yeah. So on a smooth surface or smooth-ish surface, as you get the refraction, you will also get reflection. You'll get a reflected, what color haven't I used? You'll get a reflected ray that goes roughly in this direction. So I can also describe the angle for this reflected ray. I guess I'll describe the same way I've been describing. This angle here, angle between the light ray and the surface normal. And this reflected ray, theta r. Does anyone here know intuitively how this relates to other things? Yeah, this angle of reflection is equal to angle of incidence, right? That, like, you know, when you hear that, that sounds familiar, right? As if you've heard this somewhere, or it just makes intuitive sense that this theta naught is equal to theta r. Like, it sounds true. It's like somebody telling you 1 plus 1 is equal to 2, or 1 plus 4 is equal to 5, and like, you don't question it. If someone asks you why is this true, then that's where most people would sort of be at loss for words. It's like, why should it be that whatever angle it came in should be the angle that it went out in?
Conservation of momentum. I don't know.
Why should it be conserved? I mean, it's interacting with the medium. The medium is very heavy. It can carry away whatever. Because you're thinking of a ball bouncing, right? But when a ball bounces, momentum isn't actually conserved, right? So I'm actually not going to do this part because, I don't know, too long. I like the other one better. But I want to point you to the part of the textbook that does cover it. The part of the textbook that does cover it is I'm just not going to be able to say the name right. Huygens principle. I don't know how to say the name right. So this is the section of your textbook that describes a principle that you used for describing waves, wavelets, and how you deal with that. And this principle can be used to describe, for example, propagation of a plane wave, and sort of where the law of reflection comes from. And all this picture is very complicated, which is why I don't really want to get into it. Read the textbook, however much sense it makes to you, it's great. I guess the first thing we should go over is the concept of image. It's, you'll find that if you look in your textbook, it's actually not defined anywhere. So if you go to the, let's see, if you go to the end of the textbook, and I did that because I was trying to write down, when you look at the glossary, it does talk about things like image distance. But they will never really take the time to define image. It's sort of, I think there's a good reason for it, but let's try to go through what an image is, so, because it'll be an important part of what we are talking about it in this chapter. So here's a maybe most common example of an image. I have a plane mirror here. Everything you see in this plane mirror right now is an image. So let me put this right here. So for people who are sitting along the center column, you are going to see yourself mostly, maybe your neighbor. People who are on this side, you'll see that other side. So let's see. Function, do you see Jason? Yeah. Okay, Jason, you see a function? So what you are seeing in this mirror is an image of function. So where does it appear to be? If you are, caveman and you didn't know what mirror was, as you look at this, where would you think he was? Like through here, at some far distance away, you might think this is a transparent window and there's a person sitting over there, right? So in short, that's an image. Image is a construct or abstract idea we use to describe when some arrangement of light appears to be coming from some place that it's not actually coming from. So it is actually coming from function's location. The ceiling lights are reflecting off of him. Some of that light is coming to the mirror. It bounces according to the law of reflection that you know, and it somehow reaches you or reaches Jason. That's how you see those rays of light. But if you ignore how this optical element is modifying the light, it appears to be coming from a distance, coming from a particular place. So this, let me draw a diagram because it's hard to just point at things. So if you have, let me draw the mirror here. If you have a mirror, for example, and you have something or someone over here, I guess I'll draw a triangle. Then when you look at this ray that's coming from this point on the triangle, this ray goes in many, so there's the light from here goes in many different directions. It's what we call diffuse scattering. The light that's hitting most of the object, it scatters into many different directions. I guess the contrast would be something that's in a very directional, like most of you cannot see this laser beam until I shine it directly into your eye. So this would be a single ray of light, literally single ray of light that you won't see until it diffusely reflects from my hand. But in everyday life, in most cases, you have diffuse reflection and light rays are going kind of everywhere. And for a particular person here, this particular ray of light would hit off of the mirror, and it undergoes reflection the way we were describing last week. So angle of incidence equal to angle of reflection, and someone who's present here sees this ray of light, and to this person, to this observer, this ray of light appears to be coming from this direction. Appears to be coming from this direction that you would get when you extend this ray of light. Now, when you're just looking at it, you will see that there's a question that we left off unanswered. So Jason, once again, sorry, I'm sticking with the example I've used. When you see a function in this mirror, does it appear to be at a particular distance? Would you say he's very, very, like, would you say that you could not tell if he's right here or if he's very, very far away? Or is there a very particular place where he appears to be?
He's far away.
Okay, far away as in somewhere like over here, back here, right? But one thing you wouldn't say is that you do not say that you would not say that you couldn't distinguish whether he's way over here versus whether he's over here. You can clearly see that he's not very close to the mirror, right? So when you look at your images in the mirror, they actually appear to be at a particular location, not just one point along a line, but a very specific point along this line. And when you look at this tracing of a single ray, that is not what you get, because with this single ray, like this ray could be coming from anywhere along this spot. But somehow, intuitively, when we look at things in mirror, what you know intuitively before I prove it mathematically or whatever, is that the image of this point is kind of here. Like this is where the image is. It's not just anywhere along this line. So how would you get that? How would you sort of prove that the rays of light that's reflecting off of the mirror, they do really appear to be coming from this single point, not anywhere along this line?
Because they have the same distance?
Okay, It happens to be the same distance here as here, but that sort of sounds like a made-up rule to me. As in, the rule makes sense, right?
That's the virtual image, right? The one that is...
I'll get to virtual soon enough. So what Samuel was saying was that maybe the rule is that this distance is equal to this distance, which is true enough. But what I'm looking for is I'm looking for a general procedure. I want to find those procedure or rule that I can use even for lenses, even for things that's nothing like a plane mirror. So this is what the problem comes down to. Problem comes down to trying to define a point. What geometric object do you need to define a point?
X and Y coordinates.
Okay, if I have two coordinates, I can do that. Let me rephrase my question. I have one line already, right? And the way this point is going to be defined will have something to do with this line. It'll be along this line. So what additional thing do I need in addition to this line in order to define this point geometrically?
Another line.
I need another line. When you have two non-collinear lines, where they cross can define a point. So that's what I'm going to need for here. I'm just going to need another set of lines. So graphically, this is what it is. I drew one ray. So what I should do is I should draw another set of rays. I should draw maybe another ray that reflects from not this point, but from this point. Let me do it in different color. So, the ray that's reflecting off over from here, it must have traveled in straight line from the this point to that point where it's reflecting. Right? I can draw this because I'm supposing there's infinitely many rays here. I never drew a comprehensive list of rays. I just drew a few as a representation. I'm just identifying one more that makes it convenient for me to do this. All right, this ray will undergo the same reflection under the law of reflection. And because this angle of incidence is smaller, this angle of reflection will also be smaller. So it should be drawn at something like this. No, I'm trying to draw this correctly, right? Because of the difference in angles, you see they are diverging, right? As they come to an observer who's somewhere out here, two rays are diverging. Now what you see is that when you trace this ray back, they will cross at some point. And if you drew this drawing correctly with rulers and protractors, you would see that they cross at the point where you are supposed to find the image. Yeah?
What if the second ray that you drew was like pointed that way?
Why would you?
Because you pointed them both to the right, but what if you pointed one to the left? You would get
You mean if I have this ray?
Yeah.
Well, the observer here will never see this ray, right?
Yeah.
But you know, even for this ray, if you draw it correctly, it should appear to come from this point. That is actually an amazing thing about image. Any light ray that's coming from this object, so let me actually use the term, any light that's coming from the object, and it first hits the mirror, and then goes to any observer, will appear to be coming from this image. So we will treat image, as far as optics is concerned, almost the same as object. This is a source of light, or we treat it like a source of light. Any light that first goes through some particular condition will appear to be coming from this thing that we are going to call image. Yeah. So yeah, does that answer your question, Javier? Yeah. So you can do it for any of the infinite rays, and if you drew it correctly, you'll find that they all appear to be coming from this single point. That's how we locate the image formed by a plane mirror. And I won't go through the exercise because it'll be intuitive to most of you that the location of image is at an equal distance. You sort of intuitively know where to find it. Right? Yes? So what I'm going to do instead is spend a little more time talking about image formed by slightly more complicated objects later on. A spherical mirror, curved mirror, and a spherical refractive surface. And yeah. So, all right, so Samuel mentioned the phrase virtual image, right? Yes, you said this is where the virtual image is, and you're right, this is a virtual image. What did you mean by virtual?
It has the same shape, the same,
Okay, have you seen what a real image is? Okay, a lot of people here would not have seen real image. So this is what I want to go over now. It's a distinction between what a real image is and what a virtual image is. It's a very simple distinction. I want to put this somewhere where almost everyone can. So with a plane mirror, you will only ever see virtual image. You won't see real image. So let me take this away. This is something called the Fresnel lens. What it is it's a magnifying glass. Like you can see my face magnified, right? Kinda. I can see it. Do I look like a magnified face? Yes. Okay. All right. So all it is. It's a magnifying glass. That's really what it is. It has a special construction that allows to be super thin, but just think of it like a magnifying glass and you won't be wrong. All right, so it's a magnifying glass. And right now what you're seeing is a virtual image. It's just like the thing you see in the mirror, not that different. So this is a light bulb that we actually use for magnetism in 4B, but it'll work well enough for what we want to do, I think. So let me turn this on. And you can see the light bulb. And let me just to see how, kind of have to know the focal length of this thing. All right, so right now you are seeing virtual image. For those of you who can see it, let me see if I can get it to project a real image. Sorry, to be way back here to see. All right, yeah, I think that's good enough. All right, so what I'm going to do is I'm going to flip it around. So when you're on this side, so you see the light bulb either right side up or upside down. Big deal. Sometimes it looks big, sometimes it looks small. So what I want to demonstrate is the actual difference between real image and virtual image. I can do it more easily if this room isn't so bright. So let me bring down the blinds to do that. So let me turn off everything here. I think that'll be dark enough. I'm going to flip this around so that now the source of light is over here, and I'm going to try to form a real image on this side. All right. So the optical quality of Fresnel lens isn't very good. So this is the best I can do. This is the real image of the filament.
It's still upside down, right?
Yeah, it's still upside down. So this is what I want you to imagine. When this light bulb was on this side, this lens, it actually formed a real image somewhere, let's say, over here. I mean, there is nothing physical here, but the real image formed here. And when you are looking through the lens, the light that you are seeing coming from this looked like it was coming from this location in space. Now, this is demonstrating more concretely that there is something here that's not at any other place. Like it's out of focus here, it's in focus here. So this is something that's projecting an image, projected on a screen, make it go through diffuse reflection and see it from other places. That's something that's only possible with a real image and not with a virtual image. It's because the distinction between real and virtual image is that for real image, you can do this. You can draw a ray of light coming from the light bulb through the optical element, and it actually ends up at some place where the image is. When you look at this, let me turn on the lights back.
Here is another example of a real image formed by the Fresnel lens on a white screen immediately behind it. You can see the bright sky, building, and the cars occasionally passing by. The image is formed at a fixed distance. So if we move the lens closer or farther, the image will go out of focus. I can do some tilting while the image remains in focus. And without the white screen to diffusely reflect the light that's forming the image, we can't quite see the image unless you are positioned correctly relative to the lens. Now, back to the in-class demonstration.
Maybe, oh, it's bright enough to actually do that. When you look at this virtual image from this mirror, the light rays, they do appear to be coming from here, but it doesn't actually come from here. When you have a real image, sort of imagine when it was the other way around, the light rays do appear to be coming from this point image, that's what image is, and they actually do. They actually do come from here. So that's the distinction between a real and virtual image. In both cases, you would say image is where light rays appear to come from. And I guess it's better to define just the word real. When you have a real image, not only the light rays appear to come from there, the light rays actually come from the image. I mean, originally from the object, but through the intermediate step, it actually does come from the image. So light rays actually come from doesn't sound quite right. I want to say go through. Actually go through the image. Actually go through image. So that's the distinction. Virtual would be the negation of this. Light rays don't actually go through the image. Like here, the virtual image, no real light rays ever went through this point. So when you have a virtual image, when you see something like this, you see a virtual image of this light bulb on the other side of the lens. Like the light rays appear to come from somewhere here, right? And if I place the screen anywhere here, you wouldn't see what you're seeing on the whiteboard before, because no light rays are actually here that you are seeing as a virtual image here. Okay? So that's the distinction. I want to draw that distinction now and start developing your intuition, because having this intuition will make it easier for you when you start mentioning some sign conventions and doing all this math. So what intuition is helpful for is it tells you when you are wrong. Also tells you when you are right, but more importantly, it tells you when you are wrong so that you can sort of look for what's wrong. Once you have a clear understanding of what real image is, what virtual image is, that will make it easier for you to apply the sign rules that we are going to cover soon. I think the biggest value of the simulation is kind of playing with it, noticing what's unusual about it, and kind of learning from that. And what I'm excited about this simulation is it kind of intuitively shows you some of the things you can that
takes a lot of work kind of sketching out if you are sketching things. And this new version of the simulation also has a version for mirror, which I hope kind of illustrates the reason I prefer to work with the lenses. So with the mirrors, when you're drawing ray diagrams for the mirror, it'll tend to get very messy because you can have this kind of overlapping thing and distinguishing between outgoing rays and incoming rays. So sometimes it becomes difficult. That's one of the reasons I prefer the lens description. And almost everything you can do with the mirror, there's an analog in the lens version. So I'm gonna be working with the lens. I guess the one thing that might be worthwhile pointing out in the mirror version, because I think I've seen this in some students in the past. Sometimes people want to memorize rules that are based on whether something is convex or concave, and I will tell you that that'll lead to confusion, because things that are convex in lenses does very different things from mirrors that are convex. So if you're trying to memorize the things based on whether things are convex or concave, you gotta flip them around for lenses and mirrors. And what I would recommend, and I think you see me giving this recommendation in lecture, when you're memorizing rules like sign convention, memorize it based on converging or diverging. Leaving it to your intuition whether a particular object is diverging or converging, and that kind of, it's a kind of factoring kind of thing, refactoring kind of thing, refactoring your knowledge. So in terms of dealing with the geometric optics, you know what to do when you have a converging arrangement and when you have a diverging arrangement. And in terms of whether concave shaped mirror is converging or diverging, well, that's the other piece that I would recommend having as a separate package. So let me just work with the lenses. And this is already useful to show a number of things. One is, so right now this setting is set up to show marginal rays. And when you see me do ray diagrams, you won't see me draw marginal rays. Partly because it's hard to know with the marginal rays in which way they should bend. Most often we'll be drawing principal rays, because principal rays have a very easy to follow rules that I can use to draw them. Now, sometimes with the principal rays, you will have a diagram that maybe looks a little bit unnatural, like this ray here. It's not even hitting the lens and it's still bending. It's because principal rays it's just a mathematical tool. It's not necessarily indicating that any kind of actual physical picture, depending on the size of the lens. Oh wait, that's wrong diameter. Wait, is that no, that's, well, why? Well, anyways, depending on the size of the lens, the principal ray may be hitting the lens, or it might not. Either way, what the principal ray tells you, it doesn't change. You can see it here. As I change the diameter, the location of the image doesn't change. And here, what I will say is the most physically correct view is actually this one, the many rays picture. And this is really useful when you're drawing a ray diagram for the virtual object. I think you see me do that in one of the lectures. When you're drawing ray diagram for virtual object, that's when you use the fact that many of the rays that you are not drawing, when you do principal ray diagrams, the rays that you don't draw, they are still there. And so that's the real physical picture, that there's an infinite number of rays going through the lens that originate from a point. And the principal rays are simply what we draw to help us locate the image. And I guess one last thing that might be worth noting while I have the simulation up is something kind of a change to note. And I guess note what doesn't change as you change the size of the lens. So as you make the lens smaller versus larger, So this is a simulation. It's simulating things that are programmed in, and it's programmed to illustrate a certain thing. Note how, as I make the diameter of the lens smaller, the extent of the image that's being formed here, it doesn't change. Just because I have a smaller lens, that doesn't mean only a smaller portion of the object gets imaged. The entire object still gets imaged. And as I make the diameter larger, what does change is the brightness of the image. It's kind of indicating, in this many rays view, how many of these many physical rays actually go through the lens and forms the image here. With a smaller diameter, less of that happens. That's why your image is so faint. And in the lab, you will get to see this in a more fun way, in that with this diameter, I think sometimes it's kind of easy to see. All right, so you still have the same issue lens. It's a matter of how much light you catch. So that's why the location and the extent of the image doesn't change. In the lab, you can cover half of the lens, as in cover like upper half or lower half, and see what kind of change, if at all, happens with the image. So this simulation isn't made to do that. It doesn't. I tested it before. It doesn't. It doesn't give me a barrier that I can move around. So, anyways, so I would. It's a great tool to kind of play around, see if the kind of the intuitions you have about ray diagrams match. And I'll just leave that there.
How many here know what I'm talking about if I talk about polarization of light? Some of you. How many here have ever had polarized sunglasses? Yeah. Anyone here know what they mean by polarized sunglasses? Like polarized in what way?
It's like a filter of light.
It's a filter. I don't have, sorry, I forgot to bring my polarized sunglasses. I do have these polarizing filters. This is what's on your polarizing sunglasses, except higher quality. And when I put this in front of a light source, and it's this light source, nothing happens. It just makes the light dimmer. That's not very interesting. You get something in, so it's because the light coming from the projector is an unpolarized light. So when I put this polarizing filter in, right now you kind of take my word for it that it's polarized. But when you have two polarizing filters, I can actually show you what happens when a polarized light tries to go through a polarizing filter. As I turn this, the intensity changes. Depending on the orientation of the second one, either the transmitted intensity goes to 0, or it can go to something that I guess you could call maximum. Okay. So this is a sort of quickest introduction of polarized light. And how common do you think polarized light is? Very common or very uncommon? Very common. Where do you see it, other than what I just did? Sunlight is actually not polarized, not most of the time.
Cameras have polarizing filters on them.
Yeah. Yeah. So let me pass these around. So if you have a cell phone other than iPhone, or if you have a computer screen, try looking at it through this and turn it around. You will find that it changes the intensity. Just, I don't know, try it or just pass it on. So any LCD screen is naturally polarized the way it's constructed. Apple, by the way, does things to its phones so that it appears as unpolarized as possible. It's like circularly polarized. We won't get into that. So, why are your sunglasses okay, so this is all neat, but like why would you want some polarized sunglasses? Like, that you can make the light dimmer and brighter by turning something. All right, that's interesting, but like why bother making sunglasses polarized? Better contrast. Now, it does make contrast better in a very particular way. I don't know how well you can do it. Whoever has is the sun gonna go out? whoever has the polarizing filter, can you point it, look outside the window, look for some spot where you see a lot of reflected light, and try turning that filter 90 degrees. Do you see something happening to the reflected light? What happens to reflected light as you turn it?
You can see like all the windshields in the cars, like it gets a lot dimmer.
Yeah, reflected light gets dimmer, right? It's because, so sunlight is not naturally polarized, but as it reflects, it can get polarized. So that's what I want you to go over in the next part. So everyone here has a visual image of what sort of polarized light looks like, or some in some sort of abstract sense. So everyone here, we went over light is an electromagnetic wave, right? So this is the visual image I want you to have. Sort of imagine the location of each of these rings as representing electric field, direction and magnitude. So if I have a light that's polarized this way, then I could represent it with a wave that looks like, I could represent it with a wave that looks like this, electric field that's oscillating up and down. So this would be vertically polarized light, and the other polarization that's orthogonal to this I can get is this direction. So it would be like something that's polarized this way. So polarization is something you can get from any transverse wave, like this wave on a string. Everyone here remembers the phrase transverse wave? All that means is the displacement is perpendicular to the propagation direction. The other one is the longitudinal wave. Sound waves are longitudinal wave. So the sound waves cannot be polarized because it's the displacement is along the direction of propagation. So like when you turn in 90 degrees, nothing really changes. So that's the visual image I want you to have. And with that visual image, let me try to go over what's called Brewster angle. I don't think your textbook refers to it that way. Or we could call it polarization by reflection. So this is the picture I want you to imagine. We've been using example of water, so let's say water. I have this very flat water surface, and let's say I have orange sunlight that's coming into this water. I have sunlight coming in. And let me just draw one ray that's going to bounce off of a point on the surface. There will be something reflected, and there will be something refracted. Good? And as I said twice now, sunlight is not polarized. So within this ray of light, if you look at the oscillating electromagnetic wave, you will get the electric field that's oscillating in the two possible directions that are both perpendicular to this. So one possible direction would be oscillating this way, so perpendicular, sort of up and down. What's the other way that it can be oscillating that's perpendicular to this? Yeah, in and out. So sunlight, it could be polarized in this way. Let's call that direction A. Or it could be polarized so that it's going into the board, and then as it oscillates, comes out of the board. This let's call that B. So those are two possible polarization of this unpolarized light. And as it hits here, you can sort of think of it as 50% of the light intensity is polarized this way, 50% of the light intensity is polarized this way. That's what makes it unpolarized. It's a little bit more nuanced than that, but that's good enough for us now. And what I want to describe is as both types of electric fields reflect here, they reflect differently. Let me actually step back a little bit. So if you look at the picture kind of microscopically, what produces this reflected light? Something produces it. Does the sun produce this reflected light directly? No, it's going the wrong direction, right? So I want you to go back to, so light is an electromagnetic wave. What do you need to produce an electromagnetic wave?
The change of current.
You could do it with a current.
Yeah. Or change of magnetic field.
Also still current, which is magnetic current, yeah. So I want to describe things as electrical as possible. What Gauge is trying to describe is what's called the magnetic dipole radiation. I want electric dipole radiation. I guess we don't really cover this in 4B. So you could generate this, so this wave, this kind of polarization, you could imagine that being generated by a charge that's oscillating up and down this way. That'll produce this kind of the light that's polarized this way. Or if I have a charge that's oscillating into and out of the board this way, that'll generate electric field that's oscillating that way, so the light polarized this way. Yeah? So as this electromagnetic wave hits this surface, how, so this is what I want to say. This reflected light, it's coming from the water. How does water contain charges that's going to be radiating light? Does water have any charge in it? Yes, it does. It's made up of protons and electrons. So there are electrons in water. So there are electric charges in water that interacted with this incoming light. So this light incident here, that's going to shake this charge up and down this way, or I guess a better picture right now is the charge that's charge that's here. When it interacts with the light that's polarized going in and out of the board, this charge is going to be shaking. It's going to be shaking in and out of the board. So that's going to produce light that's polarized this way. From this charge that's shaking into and out, there will be light polarized going out this way that's polarized that same way, into and out of the board. And I don't know if people remember this one particular feature of dipole radiation. When you have an electric charge and it's shaking up and down, there's one particular region where you don't get a lot of radiation. Do people remember that? Yeah, we don't really cover that. So I see I don't have a lot of time. So let me just point you to places where you can kind of experiment with this on your own. So there's a place called PhET. How many here don't know PhET.colorado.edu? So that's the website, PhET.colorado.edu. PhET, they have a lot of physics simulations. The one particular simulation I want you to look at on your own time is there's here's this radiating charge. So what I was trying to kind of gesture with my charge is if I have this charge and if it's moving at some constant speed, nothing interesting will happen. So if it's let's see, if it's linear, then it won't really generate any wave. To generate wave, you need to have it oscillating, like a sinusoidal. So as it oscillates in sinusoid, oscillates up and down, you see these waves being generated, right? There's one direction where you don't see any waves, though. This direction, right? You don't see any wave. And in an upper division electrodynamics class, you'd derive them mathematically and all that using Maxwell's equations. We're not going to do that. But I want you to just know that as a qualitative fact, that when you have a charge that's oscillating in one direction, then along this axis of oscillation, you won't get any radiation. So that's how these two polarizations interact differently. So the one that's polarized into and out of the board, as it bounces, as it's oscillating that way, there's no issue with the light being propagated this way. But for the other polarization, if you get this in just the right way, so that the light that has been refracted is going in a way so that this perpendicular direction, which is the direction that charges are oscillating, somehow lines up with this perfectly, then there will be no radiation that's going in this way that's polarized this way, because there's nothing that could be making charges shake that way. So that's the geometric arrangement. And the derivation of Brewster's angle, or the angle at which you get polarization, you work through this geometry. Your textbook does it, so I don't think I have to go through it in detail other than to just sketch it. So the way you would do it is you have this incident angle, theta 1. You have this outgoing angle, theta 2. You can relate this using Snell's law, right? And the condition you impose is, okay, I know this reflected angle of reflection, so I know what direction this is going. And this is the piece you need. You need to be able to say that somehow the angle between the reflected ray and the refracted ray is 90 degrees. Under that condition, there's no oscillation of charge in the medium that would produce the other polarization, so the light is 100% polarized. So as a matter of general sort of, I don't know, useful effect is that when sunlight reflects at a glazing angle from a surface like that, more percent of the light is polarized horizontally. So they make these polarizing sunglasses in a way to block that horizontally polarized light so that you can see better through glares. You'll see that if you turn your head 90 degrees, then you actually get extra glares because it's blocking the other light but letting through the light that has been polarized through reflection.